Hey everybody, and welcome back to part 2, Earth Spin Generator. Today we're all in for a treat. I reached out to Chris Chyba at Princeton University, one of the investigators into this Earth Spin Generator malarkey. And just like you, I wanted to know, does it work and how it works? So lovely people, today I'll share my interview with Chris. And the main thing I wanted to ask him is, why has this been kept secret for over 150 years? And that's a really good point. Chris and I are both Michael Faraday fanboys. Who wouldn't be? Michael Faraday invented the motor and the generator and was the first person to describe how magnetism can produce electricity when it interacts with a wire. But one of the most important findings of Michael Faraday has been ignored and, in fact, oversimplified. And I think that's a big reason why science, has not looked at the idea of using the Earth as a giant magnetic spin generator. We all live in a magnetic and electrical world defined by Maxwell. And Maxwell, in my opinion, oversimplified Faraday's ideas. The nub of it that you need to know, bing, is that the magnetic flux of our planet Earth is not linked to the rotation of the Earth, it's caused by the rotation of our Earth. That the magnetic flux lines of the Earth are independent from the spin of the Earth. That means you could have a device or an electrical coil on Earth that is going to pass through a magnetic force which is moving round the Earth caused by the Earth's rotation. Somehow that decoupling has been ignored until now. And Professor Chris Chyba also thinks the offset of the magnetic pole to the physical pole, so the Earth spins round its physical pole. But you all know that the magnetic North Pole is offset. In fact, today it's more offset than it's been for years. And that magnetic pole offset to the surface spinning of the axis of the Earth means that the field line will pass through a generator. Wah! Oh, calm down, Simon. Over-enthusiastic, I know. But it builds on my hero Michael Faraday's work and has been forgotten for over 150 years. So it is super exciting. And I'm not the only one jumping up and down about this. Watch this clip.
Hello, wonderful person. This is Anton, and today we're going to discuss a somewhat bizarre discovery coming out of Princeton University. And here the idea is really based on the differences between the magnetic field and the rotation of the planet. And that's because the spin of the planet is technically a little bit misaligned compared to the magnetic field. So basically here our planet has two distinct axes, and the Earth's magnetic axis has an inclination of about 11.5 degrees to the axis of rotation, which basically means that the magnetic poles and the rotational poles are not exactly in the same place. And as we know today, magnetic poles are also not really stable and tend to drift over time. For example, here's how the North Magnetic Pole changed in the last 5 centuries. And so in this recent study, once again Christopher Chyba, Kevin Hand, and Thomas Chyba, it really does look like maybe it's being produced by the magnetic field interaction after all. So there's a very high chance right now that they basically produced free energy due to the rotation of the planet.
So, today, viewers, let's actually hear from Professor Chris Chyba from Princeton University. Hey, everybody, guess who we have today? Professor Christopher Chyba from Princeton University. Christopher, what was the inspiration that you thought in the 21st century to repeat Michael Faraday's experiment? Maybe explain go over what he did, but I'm really intrigued to know what led you in the 21st century to repeat an experiment that was brilliant but didn't work.
Well, we have to understand that Faraday was groping almost in the dark, brilliantly groping. I think one of the greatest experimental scientists of all time. But he was figuring this stuff out for literally the first time with much of what he did. So he was asking questions that if they had been asked before, certainly hadn't been investigated. And he was aware that if you moved a circuit past a magnet, that you could generate electricity. And he was aware that the Earth had magnetism. So he thought, well, maybe I can construct a circuit, at least if it's big enough. And as the rotation of the Earth carries that circuit through the Earth's magnetic field, maybe I can generate electricity. He tried, but it doesn't work. And we understand very well now, centuries later, why that simple experiment couldn't possibly work.
Yeah. I know it's a fantastic experiment, brilliant, well done, well done, Faraday, for trying it. And let's just establish that we're sitting right now, both of us, on a spinning globe that at the equator rotates at over 1,000 miles an hour. You and I are about 41 degrees north of the equator, so we're about 800 plus miles an hour. So, and it's a giant ball, and it's a magnet. You know, we have a North Pole and a South Pole. So the idea of using the Earth as a rotational device, if only we could have, you know, a way of inducing that power. I mean, of course, you could imagine a giant copper grid, you know, round the Earth, and then you'd have the Earth spinning round, inducing power in a copper grid. But how on earth would something that rotates with the Earth, Faraday's piece of metal, you know, why did he think it would work, and how did you get it to work?
Right. Well, we have to remember that while Faraday was brilliant, he had no math. He wasn't a mathematical physicist. Mm-hmm. So he explored things with his experiments, and he didn't know whether it would work or not, and he was just trying to find out. In our case, it's easy to prove mathematically that the experiment he did can't work. Once you have 2 centuries of physics beyond where actually it's about a century worth, but by the time you get to Maxwell, it's clear that Faraday's experiment couldn't work. Mm-hmm. And that seems to settle it, right? It's impossible to do this. And what Kevin Hand and I realized, Kevin's at the Jet Propulsion Laboratory, is my co-author on the original theory paper.
Right.
Kevin and I realized that there was a loophole in the proof that you write down that shows that it's impossible. That under very particular circumstances that involve topology and involve materials, it should be possible to violate that proof and actually generate at least a small amount of electricity.
Oh. Right. So I'm very much in the Faraday camp, but like experimentalists build steam engines and things like that. So is it something to do with the north and south magnetic pole not being in line with the physical pole? Is that offset part of, could that be utilized? And also the magnetic field coming from Earth is a different circumference. So it's obviously going to be offset from the surface of the Earth.
Right. No, in fact, it's just the opposite of that. The part of the Earth's field that we think that we're using is the part that's symmetric about its rotation axis. Oh. So, right, most of the Earth's magnetic field is axially symmetric. That is to say, as you move around the Earth in longitude, as long as you stay at the same latitude, you see no change in most of the Earth's magnetic field. Then there are these smaller components that, as you say, are due to the tilt, and those do change with longitude. But we're tapping into, if we're right, we're tapping into the part that's axially symmetric. It doesn't change as you go around the Earth.
But the magnetic field is produced by us, our giant magnetic planet, and and the effect needs rotation. It needs that dynamic movement.
Yes, this is only
static. It wouldn't work.
Yes, that's correct. If everything were static, nothing would happen. Right. And in the 19th century, due to other experiments Faraday did with rotating magnets, cylindrical magnets that were rotating around their axis, there was a controversy over whether the magnetic field of a rotating cylindrical magnet rotates as the magnet rotates. Does the field rotate with the magnet, or does the magnet rotate through its own magnetic field? Right. And he invented this Faraday generator, sometimes called a homopolar generator, where he could produce electricity with a rotating magnet, just that way. But then later in the 19th century, it was still controversial whether that was because the magnet was rotating through its own magnetic field, or the field was rotating with the magnet, and as the field lines of the magnet passed the rest of the circuit, they caused the electricity to be generated. Faraday had the opinion that his magnet was rotating through the field, but 30 years later, a scientist named Preston, who did have mathematics, was able to show that with the other assumption, the mathematics showed you got the same answer either way. So this was a controversy until the early 20th century,
Right.
when a set of physicists based in the U.S. figured out how to adjudicate between those two views. Does the field rotate with the magnet, or is it stationary and the magnet rotates through its field? And they showed decisively, this is Barnett and Kennard and Pegram, in separate experiments, separate laboratories, they showed decisively that the field does not rotate with the magnet. So the magnet rotates through its own field. That's what generates the electricity. And that suggested to us that here on Earth, we must be rotating through our own field as we rotate with the Earth. We're going through the Earth's field at, as you said, 350 meters per second at my latitude.
Oh, that's fantastic. Oh, let me just get this, my kind of simple physics brain right. So you're saying that the Earth's magnetic field is stationary, and we're on the rocky bit are going round.
The part of the Earth's field that is axially symmetric is stationary, and we're moving through it at 350 miles per second. Yeah, 350 meters per second.
Yeah. 350 meters per second. We've got a generator, potentially. But I like it. But when Michael Faraday did his experiment, what did he use? I take it he used an iron rod.
Well, he tried. I mean, he did various experiments. I think the one we cite to in our paper is an experiment where he stretched a long wire, basically stretched a long circuit, and hoped that maybe that would generate electricity. But there's a problem with that approach. Suppose you used a rod. Suppose this is just, I don't care whether it's iron or not at this point. It's a conducting rod, say. And so it's moving with us at 350 meters per second through the Earth's background field, the magnetic field of the Earth. Actually, here in Princeton, the field's coming down this way, so I should tilt.
We'll talk about tilt.
Perpendicular to the field. So it's moving through the field. And that means there is a magnetic force which is proportional to the velocity we're moving times the strength of the magnetic field, and it's trying to push electrons this way. Let's see, V cross B. Actually, it's trying to push electrons this way.
All right.
Okay. So, but then what happens is the electrons do move, but they move extremely rapidly. You can calculate the time scale for that, and for an object like this, it's a billionth of a second. They spend redistributing themselves, and then once they redistribute, there are more electrons down this end than there are up at this end, and that causes an electric field that points in this direction that perfectly cancels the force from the motion through the magnetic field. And as soon as that happens, and that happens in a billionth of a second, it's game over. Nothing more happens.
There's no flow. There's no, you can't utilize that initial jump. It's gone.
Right. It's so short, it's useless. And you should think of the electrons in this tube as in this metallic cylinder is continually just redistributing themselves on this ridiculously short time scale to perfectly cancel the magnetic force inside, so nothing can happen. And that's why Faraday's experiments couldn't work. I mean, he did many other experiments that worked brilliantly, but this effort on his part couldn't possibly work.
Sure. So after reading your paper, Chris, it seems that material science comes into the next element of how this might work. Maybe the electrons can move slower. Is that part of it?
There are two things that are needed. And one is topology and one is materials.
What's topology?
Exactly. So this isn't a solid tube, it's a hollow tube.
Oh, yeah.
Okay. Topology is the field of mathematics that describes, say, why this hollow tube is fundamentally different from a solid tube.
Okay.
I can't start with a solid tube, and unless I tear it or break it and then fuse it back together again, I can't turn it into a hollow tube. I can't turn a sphere into a donut, not without tearing it. I can turn a sphere into an American football, right? Those are, in that sense, those are topologically identical. But if I want to turn it into a donut, I have to break it, right? So topology is a field of math that studies those differences. And the first thing we realized was that if you're conducting material has this kind of shape that, and if it also has magnetic properties, you need those two things together.
Right.
That the electrons actually cannot redistribute themselves to cancel the magnetic force. You can prove that mathematically. They can't do it. It's still, I think, is just remarkable. It's remarkable to me that they're trying, but they can't do it. And that's a firm mathematical proof.
Sure.
And therefore, that opens the door to the possibility that you could be generating currents inside of this thing because they're unbalanced forces.
They're unbalanced.
It opens the door. It doesn't guarantee the result, but it makes it possible.
Right. But they do, even the unbalancedness would happen very quickly. So you needed a special type, you chose a special type of material that had a special effect, an electron effect, a well-known material. What was that?
A material that's existed since the 1940s, yeah.
Right.
Yeah, there are two things that have to happen. One is that the material has to have a particular type of topology. A hollow cylinder probably would work with a hollow sphere, but I haven't actually worked the math through for that case, but certainly for the hollow cylinder.
Right.
But then if the material has, so technical jargon for a minute.
Yeah, go ahead.
Technobabble, if it has a high magnetic Reynolds number, and that means that the product of its magnetic permeability, which is how good a magnet it is, times its electrical conductivity, times the velocity, which is set by our latitude on Earth, times its size, its sort of characteristic size. If the product of all those numbers is big, then it turns out that the currents won't flow. That's another mathematical demonstration. Okay. And for any reasonable metal, like this object, this is mu metal, but that means it's mostly nickel and any reasonable metal at this sort of scale, laboratory scale, it has a huge magnetic Reynolds number, and there's no effect. So the only way to get an effect is to find a material that has a low magnetic Reynolds number. And as a practical matter, so we spent some time trying to figure out whether there was anything that was conducting but would have a low magnetic Reynolds number at a scale we could work with easily in the lab.
Right.
We're nanofabrication specialists. It's possible that you could do these experiments by fabricating really small objects, but we don't have that expertise. And it turns out there's something called manganese zinc ferrite.
You broke open your old transistor radio.
Ferrites are used in the cores of transformers. Yep.
Right. And antennas and a sheet plastic radio, because they have the same useful property.
They have a lot of common applications.
Right.
And they're conductors. They're ceramics. They're not really metals. They're ceramics. They're conductors. They have the conductivity of seawater, which is about the same conductivity that you and I have, right? We're basically seawater. Right. So, and that's a conductivity that's 1,000,000 times lower than this object or copper or aluminum, say. And that's what gives us our low magnetic Reynolds number. And if you have that paired with this topology, we predict that you should generate electricity. But you have to have both those things. As you would imagine, we looked at a lot of different ferrites. Even most of the ferrites give you a large magnetic Reynolds number. So actually, you have to look pretty hard, and you have to have the right topology. But then,
But then you also worked out you need to know where the flux of the Earth's magnetic field is in your hometown, where you're going to do the experiment. So the angle of the of how we move through the field, how it moved through the field, is also important.
That's correct. And that's actually a good thing from the point of view of the theory and experimentally testing the theory, because, we're scientists, and that means we test, we come up with an idea, but then we test it in the lab.
Right.
And our theory predicts that if the object's oriented this way, it'll produce our current or produce our voltage. Take your pick how you want to characterize it.
Right.
Let me label one end of this object. Let me put a little pink label here at the top. So we know what I'm talking about. Okay, so here where I am in Princeton, the magnetic field of the Earth is coming down this way. Here's the object. At this orientation, the object's going to produce small voltages, minus 18 microvolts.
Yeah.
If I rotate the object this way, and we build a turntable so that our we measure both temperatures and voltages. We have 3 voltmeters connected to this thing, measuring those.
Yeah.
They're all on the turntable. The whole thing rotates together. Okay, so nothing changes except the orientation relative to the Earth's rotation. And here in Princeton, where I'm oriented the way I'm talking to you, we're moving that way.
Right.
We're rotating that way.
Right.
So if I rotate the object to be parallel to our direction of rotation, the voltage should go to 0.
0.
And if I rotate the whole turntable around to this direction, so 180 degrees away from where I started, then the voltage should come back, but now it should be positive.
Right.
And another 90 degrees, it should go to 0 again. Back this way, I recover the voltage, but now it's negative again.
Negative.
All right, so that's a pretty strong. That's not the only test we did, but that's a pretty strong test of the idea,
Right.
because batteries don't behave that way. Lots of things don't. They don't change their voltage under rotation. But then the other thing that the theory predicts is that if I get a manganese zinc ferrite cylinder that's identical to the one we did the experiment with, but solid, completely solid, because it doesn't have the right topology, where however I rotate it, it generates 0. All right.
Right.
And we show that in the paper too. So that's another test.
Oh, I think that's fantastic. So of course, so the orientation, the shape, and but the orientation you must have predicted, and when you twiddled it, it changed polarity.
Yeah. So you rotated 180 degrees, you change the polarity. That's right.
As you thought about it before, you thought about that, built the turntable, did it, and it worked. That's fantastic.
Yes, we predicted all these effects in a paper we published in 2016.
Ah, right.
Right. And then the paper didn't get any traction to speak of, and we decided we would do the experiments ourselves to test it. But these are testing predictions we made almost a decade ago now.
I'm sure, but then we love experiments. We love the proof in eating our puddings, and so when you did it, it worked. So fantastic. But the effect it's producing is microvolts. Is that correct?
That's right.
Right. But there are many devices in rural areas that can't be maintained, don't have solar or other forms of power. Even a microvolt or a series, a microvolt kind of step up thing could be useful for us on planet Earth, potentially.
So I think the voltage or the current or the power, whatever way you want to describe it, needs to be substantially increased for this to be useful.
Right.
But so far it's been the 3 of us, in an ad hoc laboratory with almost no investment at all.
Right.
There are several things that need to happen. The most important thing is that another group, independent of us, reproduces our experimental results or refutes them. If it turns out we've somehow done something wrong, this is science. Let's find out. That's the most important thing, to have another group test this. But if another group shows the same effect, then we need to figure out how to scale this, to scale it up to get higher voltages. And we speculate on ways to do that in both our 2016 paper and our 2025 paper.
Yeah.
And the equations that we derived in 2016 that tell you what the voltage and the power should be basically act as a guide to tell you how to do the scaling. So I think the most obvious way is that you would take the device and shrink it down. If you shrink it down, you could start using much more common materials because you'd reduce the electrical conduct. You'd increase the electrical conductivity, but you'd reduce the size. You do those in tandem. So you miniaturize this thing, and once you miniaturize it, you could put many of them in series with each other. A
series of them, right?
And boost the voltage.
Yeah.
Waving my hands like that and saying the equations say it ought to be possible is completely different from actually doing it and demonstrating that it works, right? But that's step 2. Step 1 is somebody else reproduces it.
Yeah.
Step 2 is let's figure out how to get more power out of the thing.
And wouldn't it be fantastic if this experimental research was done at people at different latitudes? Because immediately you could, it would go, oh, mine's 67 and mine's 82 degrees. So,
You're right. That's another test.
Right.
The higher the velocity, the higher the voltage, and in a very predictable way. So at the equator, the voltage should be highest. If you actually did this right at the North Pole, there should be no voltage at all.
Right. There's no rotational. Right. It's so fantastic. So So probably at its very best, it's going to be maybe a couple of volts. You're not going to plug your house into it.
Right. I don't know how to predict what's possible and what's not.
Engineering, right.
We just have to see. And again, it may be that we can't scale it. We have to, that's in the next stage.
Oh, it's so interesting. Explain to me, I didn't quite understand why. I kind of get it, but just tell me in a different way, Chris, why miniaturizing it, making it out of other materials that are tiny would help.
Right. So let's imagine, this isn't manganese zinc ferrite, this is mu metal, but the object we did the experiments with in our lab are roughly this size, but made out of manganese zinc ferrite.
Right.
One way to increase the voltage would be to put a whole lot of these in series. But we would, if you want a volt, say, to light a flashlight battery, you need 100,000 of these. And that starts filling up the room I'm in.
A big box.
That's the practical device.
Right.
But the theory tells you that this works as long as you have a low magnetic Reynolds number.
Right.
And the magnetic Reynolds number is a factor of several things. One of those things is the electrical conductivity, and the other is the size. Actually, it's the diameter of the thing.
Right.
Not but the diameter. It's the length scale over which the magnetic field is diffusing in the object. Okay, so the obvious way to solve the volume problem, I don't want to fill my entire house with these things to generate a single volt, is to make them smaller. But if you make it smaller, that's going to reduce the voltage unless you also increase the conductivity to keep the magnetic Reynolds number the same.
Right.
So if you make this thing small enough, you don't have to use manganese zinc ferrite. You could just use iron.
Oh, wow.
Or some other well-known, use mu metal.
Right.
Like this is mu metal.
Right.
But then if you wanted to do this with mu metal or iron, you'd be increasing the conductivity by a factor of 1,000,000. So you have to increase the size by about a factor of 1,000,000. So you get to things that are, instead of a centimeter across, that are now you can do the math. Right? That are now a micron scale, say.
Right.
A millionth of a meter, roughly. Maybe even a little bit less than that. But there would be intermediate steps too. Use something that has conductivity between the two, and you don't have to make it quite that small.
Sure.
So that's why miniaturization is one way you could go for a practical device. Seemingly, none of this is demonstrated. It's all.
Have you been approached by DARPA?
No, we have not been approached by anyone at this point.
Oh, it's great. Well, I think it's absolutely fascinating that you and your team have actually taken what was pretty an interesting idea of Michael Faraday's, and now in the 21st century actually seen a positive effect and understand the physics of why it didn't work and now how it always did work. And I think it's very, very exciting.
Thank you. Faraday is an incredibly inspirational figure. If you read his diaries, I feel the same way reading his diaries as I feel, say, reading some of Einstein's relativity papers, that this is a person who seems to have access to a different dimension of knowledge. It's just, not a normal human being.
Oh, he wasn't a normal human being. And of course, even Albert Einstein himself was totally inspired by Michael Faraday. And, he
had a portrait of Faraday on his office.
Right. Oh, did he? Oh, well done. That's fantastic. Well, I think we covered everything. This is really, it's really great. What's the next step?
I think the next step for us is to do some further tests of the idea. Again, what scientists do is to try to falsify their hypotheses.
Right.
There's some obvious experiments we could do if we can get the manufacturer to produce them for us. One of those is that if you can increase this is going away from a practical device, but it's in the spirit of testing the claim. If you could increase the diameter of the object, then you predict a different voltage. So we'd like to have the manufacturer produce a very similar object, but of different diameter and demonstrate that we get the predicted different voltage. And if we got, then I think that would lay the doubts to any doubts to rest. And
can people at home try it? Do you think if they got a sintered piece of magnesium zinc ferrite? I mean,
well, the difficulty is getting it to be a hollow cylinder.
Yeah, can you drill it?
In our case, the manufacturer had to purchase with our funding a water-cooled diamond drill to drill out manganese zinc ferrite rods. That's the challenge, I think. But if you can find a manufacturer that's producing them, yeah. However, having said that, though, at the scale we're doing it, these are microvolts we're producing.
Sure.
Your typical voltmeter is not going to be measuring microvolts for you.
Right. You need a piece of kit that can measure microvolts, right?
You need a very different, a typical good voltmeter maybe measures down to millivolts. And then you need a whole different level, a sort of laboratory level device to measure microvolts. So that would be the next hurdle. And that comes with some expense.
Okay, but so you need a diamond drill, an old transistor radio, and a laboratory microvolt meter, and a box. And know where you are in the world.
None of this is elaborate technology. Let's be clear about that. It's not terribly expensive as a modern research.
No. I think it's groundbreaking. I think it's absolutely fantastic, and it's also very kind of understandable. I think I can see it built into things in the future. If it could be made in a kind of nano way or made in a series to increase the power output, that would be fantastic. So congratulations.
Thank you. That's very kind. Again, it's only groundbreaking if it's right. And I think we still need more experimental verification.
All right. That's great. Well, thanks for your time, Chris. That's really brilliant. That's great, Chris. Thank you very much for talking to me on my humble YouTube channel. Viewers, you can do the experiment at home. Chris is very keen to get people from the equator to the North and the South Pole to do it and see if the effect works. And what was the angle that they have to put the ferrite bar to actually produce an effect. If you want to do this at home, there's a couple of things you need to know. First of all, you need to get hold of a ferrite rod. They're pretty easy on eBay and Amazon to buy, or stick together a number of chokes which are already drilled out and hollow. That's something I'm going to do. You need to work out the angle of where your country interacts with the field lines of the Earth. And you need one special piece of kit. Unfortunately, a multimeter won't work. You need something that can actually measure microvolts, which is a piece of laboratory equipment. But micrometers are very common in a laboratory setting. You can pick them up for almost nothing on eBay, or you can buy a new one as a school supply. So go out and build one and share your results here with me, and I'll share them with Chris at Princeton University. How exciting. Now, this is going to be something very special. I've never done this before, but tomorrow, that's Saturday, I think, I'm going to do something called a live stream, if I can figure out how to do it. You've asked a lot of very smart questions, and I don't have the answers now. I might have some of the answers, and I can talk a bit more about it in a live stream. So 6 p.m. Central European Time, Paris time. That's 5 o'clock in Britain. And at some ungodly hour in the United States, I'll attempt to do a live stream and answer your questions in the comments, in chat. When it's finished, I believe it's recorded. So if you're still in bed, you can watch it later. Bah. So hopefully join me here tomorrow at 6 p.m. in Paris time, and we can chat about free Earth generators. How brilliant. The truth is out there.